Hello everyone, this is Philadelphia Bridge Restoration Team. Our team consists of Dr. Miller, and he's our advisor. Kofi, he's our team leader. Sam, Aziz, and me are the team members. For our bridge, we were considering a reinforced concrete bridge, which is on 41st between Girard and Poplar Street. That bridge was closed since 1997 due to many defects, such as random cracks, rusting, loss of minor sections, and actually 60% of the caps were fallen down. The bridge consists of 3 slabs, 79 feet, 64 feet, and 97 feet as measured from north to south. The roadway width is 40 feet with 10 feet at each side as sidewalks, and the vertical clearance is 20 feet. Our overall objective is to prepare a complete design that will be used to be replaced in the current bridge. The design will include designing the different parts of the bridge, designing a rainfall runoff model, preparing recipes, concrete recipes, and test them to meet the specifications required, and test our model when we apply the various load acting on it and see if it can withstand the various loads. And here, as you can see, an overview of our bridge. Before designing, we had many challenges. One of the most important challenges we faced was the soil load bearing capacity. This is crucial since it indicates the weight of the bridge and the amount of saddling of the soil. The current side of the bridge doesn't have any saddling, meaning that the soil and the foundation were able to hold the weight of the bridge. So when we were designing our bridge, we had to stay with the same weight properties of the current bridge. And as you can see here, these are the capacities at the north abutment, south abutment, first column and second column. One more technical challenge that we have to face is to communicate with different companies, as there are utilities running down the bridge. Companies such as Philadelphia Gas Works, Philadelphia Water Department, Philadelphia Electric Company, SEPTA, Amtrak, and PECO. For SEPTA and Amtrak, we'll ask them to detour their railroad which are running under the bridge, and for the rest of the companies, we might ask them to shut down their services just during the construction phase for safety purposes. And when we started designing, we had to decide 2 things, like the types of our bridge and the construction method. As you can see here, this figure has the different bridge types depending on the length of on the horizontal length of the bridge. And as our project, which is 242 feet long, our bridge has been fallen between for like girder type of bridge and segmental bridge, as girder is going from 125 feet to 350 feet, and segmental going from 150 feet to 500 feet. And here's a comparison between girder and segmental type of bridges. Girder bridges are simply bridges that has girders on top of the abutment and the piers with slabs that covers the entire surface, while segmental bridges are made from small sections. One section is each section is constructed at a time, and when completed form a whole bridge. And the advantages, if we want to compare between girder and segmental, girder can be made using concrete or steel. Components can be fabricated. Slabs can be replaced without much difficulties. Design can be easily modified. The problem with this type of a bridge is if long span are used, deep sections will be needed. While for segmental, it has high durability, stands for many years before needing extensive maintenance, and it's optimal for bridges with long spans. And for our construction methods, we had to compare between two methods, precast concrete and on-site concrete. Precast concrete, the parts will be constructed in a plant and transported to the site, while the on-site casting, the concrete will be mixed and proportioned off-site and transported to the site by cement trucks. If we want to compare between the two methods, precast concrete has higher quality and more stability, made under controlled condition, and that's gonna help us in minimizing the time, as we don't have to worry about the weather, and also to get better quality as it was built in plant, and it also has lower cost. For on-site casting, it has lower quality and less stability, made under uncontrolled conditions, more time, it takes more time, and it has higher cost. For our proposed solution, we have chose to use girder bridge as a type of our bridge, and precast concrete. We chose girder bridge because it's more efficient for short spans, and also since we have short spans, long sections are not needed. And for the precast concrete, it takes less time, and we really need to minimize the time, as we are dealing with different companies, and they will change. They have to shut off their services during the construction time. And for our constraints, we have dimensions constraint. We have to stick with 242 feet as a total length of our bridge, since our bridge is over a valley. Also, the length of the spans should be the same, as it's constrained with the width of the railroad running down the bridge. Also, vertical of 20 feet would be needed, since there are trains going down the bridge. Also for loading, Philadelphia, the city of Philadelphia has specified 3 tons as a limit on the bridge, and also PennDOT has specified 5,400 tons as a weight of the bridge. Drainage, we have to maintain 2.9 cubic feet per second, which the bridge should drain. And for testing our concrete recipes, should be at least, like the compressive strength of the concrete recipes should be at least 4,000 psi. And here are our technical design constraints: safety, survivability, economy, and appearance. This is, and like in designing, we have to consider the span length to depth ratio, as it is will help us in control, as it is controls the deflection. With the ratio of 20 to 20, it just gives us a starting point to estimate the depth of the slabs. But if the ratio exceeded 20, it means that there is high deflection on the beam. And as we can see here, the last span had more than 20. So we had to increase the depth of the slabs to be 5 to decrease the ratio, and we did, and we got like almost like 19.5, which is good. And here is our design deck, our bridge design deck. There are 3 types of reinforced concrete bridge decks: solid slab, void slab, beam and slab. For our design, we're gonna use void slab and beam and slab. Here is the design of reinforcement. We have the compressive strength, which is 4,000 psi, and yield strength, which is 60,000 psi. And we got the dead load, live load, wind load from our Static Pro analysis. Here is the distributed load formula from the AISC. First, we got we used the first formula with dead load and live load, and we got 1.88 kg per feet. And we added, for the second equation, we added wind load to this equation, and we got 1.7. For the first span, we have here the formula of the factor design moment. We pretty much have all the variables we need. This is length, and this is what we talked about, the factor load, and we got that number over there. And here we have this equation where we have all the variables from the previous calculations, and from and one of them was here the resistance factor, which was 0.9, and we're left with BD squared equals to 20, like almost 22,000. So we have tried B to be 20. We have tried B to be 20 to be 20 inches, and that gives us D of 33 inches. Then we got the area of the steel, which is 11.22 inches. So we have tried 3 number 18 bars with area of steel of 12 and beaming of 15.4 inches. Then we check. In design, it's usually we just assume, try, then check. Like in our calculations, we didn't get this this design from the first time. We had to check and to try and check if it's work or not. So here we got the depth of stress plug of a beam, which was 10.58, and here we have to compare between the nominal strength, the nominal flexure strength multiplied by the resistance factor, which is 0.9, with the moment here, and it was greater actually, which is okay. And also we have used this formula for the area of steel, and it was less than AS. So our design for our beam was, and that's what we're going to use, which is 3.18. The same thing with span 2 and span 3. It's the same formulas. And for bearings, just to point that bridges are not statically, so parts of the bridge can move as the temperature goes up or goes down. To control that movement, because it causes many problems if it's not controlled, we have used bearings. There are 2 kinds of bearings: fixed bearings and expansion bearing. Fixed bearing is to hold the members in place, and expansion bearing is to allow or permit some movement. And here we're using a fixed spot bearing for north assembly, guided bearing for piers 1 and 2, and elastromic bearing for south apartment. Here we have the design of the bearings. We have the load, which we get from our Static Pro analysis. Here we have the maximum vertical load, which is the forces divided by 2, and then we had all these dimensions here. As you can see, this is A, B, C, and also for this landing phase. Also, here for guided bearings, it's the same thing, the same kind of doing this, and also for the elastromic. We went through 6 steps to design our elastromic bearing, and we got 10.5 inches by 10.5 by 3 inches. Here's our drainage analysis. We use the rational formula for the 3 decks, and We got the grate inlet drainage and the pipe inlet, which was greater than the flow rate, so our design was passed. And here is the soil test, as we just talked about it, that there was no saddling, so it was okay. We have created two recipes with two different ratios here, like coarse aggregate to fine aggregate ratio and water to cement ratios. We have used the 3-day, we did 3-day test for the first recipe, and it didn't pass the test as it was less than 4,000 psi. Okay. For the second recipe, we did a 28-day test, and the compressive strength here was over 4,000, so it passes. Except this sample didn't pass because it was made of recipe 2. And here is our StatPro analysis when we applied all the loads, and our deflection wasn't that high, so which means that our bridge can withstand those loads. And here are the different components of our bridge, given a hollow bridge of this shape. And this is our schedule during the semester, and that's it.
Questions?
Yeah. Could you go back to the slide where you showed the allowable load on the beam? I think it was 3 tons.
Oh yeah. It was at the beginning somewhere. It's in the constraints. Yep. Right?
Yeah. Now, it says maximum vehicle load of 3 tons. That means that the vehicle, the heaviest vehicle that can go on the bridge weighs 3 tons.
No, it's the peak of the vehicle on top of the bridge. That's what the city of Philadelphia has specified, that the bridge should withstand with the peak of vehicles on top of the bridge.
Yeah, but you're saying the vehicle weighs 3 tons.
I'm sorry, it's not the vehicle, like the total vehicle. The total vehicle weight.
What I'm thinking is that that's the weight that they put on a bridge that is in bad condition. It's a limit. It's a load limit on a bridge. It is 3 tons for any vehicle.
Yeah, I mean, the city of Philadelphia has specified a limit to the load on top of the bridges.
Okay. Just want to verify.
Yeah, that's fine.
Okay.
Other questions? When you were talking about cast on site versus precast,
Yep.
why would anybody ever use cast on site? I mean, looking at your assessment, is there any reason why you would ever cast on site?
Right. I mean, the way of how we created this slide is different than comparison between girder and segmental. We pretty much just compare between them. Like, we didn't put all the advantages of the of on-site casting. We just put each advantages here. What does it what it is on the other method? So it's just comparison, not like showing all the advantages of the two methods.
But can you give me an example of when you might choose to use on-site casting?
Probably if shortening the time is not necessarily, and for larger bridges, because as I just mentioned, that precast concrete take less time. And especially for such a small length spans, precast concrete would be better for us. Would be more suitable for us than the on-cast concrete. But the on-site casting concrete is better for large bridges.
Okay.
Because I mean, can I add something?
Sure.
I mean, even if you wanna like, if we wanna like create the components of a very large bridge, no one would do it in a plant, you know. So it should be off-site to be created.
And one other question on the slabs, because you talked about a void slab and a beam slab. Here, yeah, three types: solid, voided, and beam and slab. So can you explain the difference between those three?
Well, like as I just mentioned, in our design, we just used voided and beam. We got the advantage.
So why did you not use solid?
Okay, yeah, I think because our depth is not that big, so solid. That's what I think. I mean, solid slabs would be for like greater depth of the slabs.
Okay. And what exactly is a voided slab? Can you
It's just
explain
like
that?
in our design document, we showed the difference between, like the different figures between them. Like the voided was all like circles all along like the deck. It was like voided. I wish I can show you a picture from our design document, because the three tabs were there, like the figures of the three slabs.
Okay. All right. Any other questions? Oh,
Just a quick one. So the old bridge, is it salvageable? Like it can't be used at all, like the old bridge that existed?
Well, it's closed for all vehicles, but like people can just walk. It was closed by barriers. I mean apartments.
anything else? Okay, thank you very much.